let's take a look at how we would go about solving polynomial inequalities. In other words, an inequality that looks like this. We're wanting to find the regions for x that when we plug in any value from those regions, any x value from those regions, we get a negative value for the polynomial or 0. In other words, if you look at it graphically, we would say, well, I'm trying to find what values for x will will result in a graph below the x-axis. So let's proceed this way. Without looking at the graph right now, let's just think about let's think about where this graph is just 0, because it says less than or equal to 0. So, and wherever this is equal to 0, that's going to be a transition point, right? Because polynomials are continuous. If your polynomial is negative, before it can be positive, it has to be 0. Likewise, if it's positive, before it can be negative, it has to be 0. So these values for x where the polynomial is 0, those are boundary points of these regions that we're looking for. So let's find the values for which this polynomial is equal to 0. And that's easy for us because this is already factored. And we can see, well, 1, that's 1, right? If x is equal to 1, that will give us a 0 here. 3, that's another one. And negative 3. So we're just solving an equation that we've done many times. You know, we've solved equations like these many times. If you're looking at a factored polynomial, it's very easy to find the zeros. Or in this case, these are actually the x-intercepts. Now, what we've done here is I've divided the number line using these boundary numbers, -3, 1, and 3. And that divides the number line into 4 regions. Everything to the left of -3, everything between -3 and 1, and everything between 1 and 3, and finally, everything bigger than 3. So I'm going to pick representative numbers from each one of these regions. So we've got -4 over here. I just needed any number less than -3. Here I need any number between -3 and 1. 0 is a good one. It's easy to work with. Any number between 1 and 3, I'll pick 2. Any number bigger than 3, I'll pick 4. Now, what we want to do then is I want to plug these test values into the polynomial and see if they satisfy the inequality. Because if I plug in a -4 and it satisfies the inequality, I know I found my solution, part of my solution. Now let's take a look at the graph, just so that you can see what we would expect to happen. Notice over here, less than -3. In this region, the polynomial is below the axis. So this is part of our solution region over here. So right away we know that when we test these values, when I plug in a -4 up here, I'll get a negative. Likewise, when I plug in the 0, notice it's above the axis. So that's not going to be less than 0. If I plug in a 2, below the axis, negative, I should get a negative. And then when I plug in the 4, no, that's positive over here. So in other words, I'm putting the graph up here so that we can kind of see how this compares to the method that we're using here, this testing method. So look, I'm going to make a table. I've got my a column for the x's and then a column for the polynomial values. Now let's start off with the -4. If I put a -4 in place of x, let's see what happens. I get a negative, and a negative. 3 negatives. 3 negatives, that's less than 0. So yes, that's part of my solution region. So look, I put the graph up here so that we can kind of compare, because this is just one method for solving this inequality. If you can look at the graph, you can immediately, get these regions without doing all this testing. Okay, it's not, but this is just a different way of doing it. Now let's look at the 0. Put in a 0, test those values, and we find when we plug in a 0 here, we get something positive. We get a negative times a negative. That's positive times another positive. That's greater than 0. Now, if I put in the 2, I get 2 minus 1, 2 minus 3, 2 plus 3. Okay? Now look at this. This is positive times negative times positive. That's one negative. That gives you something less than 0. So that's part of the solution. We were looking for what will make this less than 0. Now finally, let's put in the 4. We get 4 minus 1, positive. 4 minus 3, positive. 4 plus 3, positives. You multiply 3 positives together, and you get something greater than 0. So our solution is going to be this region over here, everything less than negative 3, and then everything between 1 and 3. So our solution regions would look like this. Negative infinity to negative 3. And because it's less than or equal to, we include the boundary point, right? So I'll put a little bracket there. Unioned with 1 to 3. See? 1 to 3. Now, it's important to remember you're not putting in the boundary numbers here in your solution. You're putting in you're not putting in the test values. You're putting in the boundary numbers. See? 1 and 3, not 2 or anything like that. Now, notice this was less than or equal to. What if I change it to greater than? Well, the same process would be involved, except you would find that these two are your solution regions. Or these two are, well, this right here is a solution region, and this is a solution region. See, and looking at the graph, you can see, yeah, that's where the graph is above the axis. Over here, the graph is above the axis. And you would get a solution, a union of these two regions. See, negative 3 to negative 1, that's right here. And yeah, you can see clearly it's above the axis. And then 3 to infinity. Now, so you can see this little method that we're using, this, making a table and testing values from each of the regions, that's the way we can come up with these, the solution regions. But also you can look at the graph, and if you know the x-intercepts, you can just eyeball the graph and then write your solution region using those x-intercepts. Okay, now let's suppose we've got something like this, and this one is different from the others because we can't readily see what the x-intercepts are, and it might be difficult for us to find them. So what we can do is we can solve this one just using this graphing method that we looked at before. So let's check that out. What I've done here is I've put that function in Desmos, and remember what we're doing, or that polynomial, we're trying to find out where is this bigger than 0. Now graphically what that means is where is this graph above the x-axis? Well, here it is, and we can see, it's above the x-axis here it is right there, and also over here. Well, what we need to be able to do though is we need to be able to describe those regions using the x-intercepts as the boundary numbers. So let me find those. I just click right here. There's one x-intercept. Here's another one. So we can see from negative infinity to negative 3.047, that's part of our solution. See this over here. Also, look at this. Okay, there it goes. Okay, also between negative 1.492 and 0.379, that's also part of our solution. That's where the polynomial is above the axis. And then finally over here, from 1.16 to infinity, the graph is forevermore above the axis. So here's what we've got. We've got our solution region right here. See? That's it. This is what we talked about. I just brought it over here and written it here. Now, let's look at how we would perform this operation with the calculator. So here I've graphed the function. Okay, here it is. And the question is, well, how do we get these x-intercepts? Okay, with Desmos it was easy. Okay, well, here's what we do. We're going to go second calc, and we want zeros. So I'll pick 2. And now, let's suppose I want this 0 right here. Or for simplicity's sake, let's just say this one. Notice it says, well, I want to move my cursor, and it says, give me a left bound. So what we want to do is we want to kind of box in where this 0 is. So here it is. Notice my cursor's to the left. I want this 0. I'm going to say enter. And notice it immediately says, okay, well, what about the right bound? So I need to move to where I'm to the right of where it crosses that x-axis. And I'm clearly there. So I'm going to say enter. And then it says guess. Well, I'm just going to move back 1 step to the left and say enter. And look, here it is, 0.379. That's how you find these x-intercepts when you're working with your calculator. And of course, I would need to do that for each one of these. This one, this one, this one, and this one. And then we could write our solution.